The next presentation will be from the TerraMeta project. So it also stays in the realm of terahertz and sub-terahertz. And the presentation will be given by George Alexandropoulos from the University of Athens. George, the floor is yours.
Hi, Hank. My greetings to the attendees and the rest of the speakers. Please let me know if you can see my screen.
So far, we see you. And we see your screen, not yet in presentation mode. Yeah, perfect.
You see the presentation, right?
Yes.
Okay, so hello to everybody once more. So in a way, this presentation might be relevant to one of the questions raised before about risk and passive risk, etc. And if it's passive by design, it's an interesting discussion. So I will elaborate along the progress of the TerraMeta project, which is actually an SNS project of phase 1. And my presentation will be around the technology of multifunctional RISs and ISAC that we're working in the framework of this ongoing project. So TerraMeta is a project that is around in its mid-duration right now. Very recently, we passed very successfully actually through our midterm review. And here you see the consortium. It's comprising of around 13 members, ISAC, University of Athens, University of Oulu, Dell Technologies in Ireland, CELET in France, Technical University of Braunschweig, University of Hertfordshire, the Instituto de Telecomunicações in Portugal, ACST, which is our SME, British Telecom, the University of Luxembourg, Intracom Telecom, and Nova. And I will describe you the outline of this presentation, which is first, we're going to go over an overview of the project in a nutshell, the vision and technological advancements, the technical approach we're following. I will actually spend more time on the multifunctional RISs and what this is about. And then as a summary, the achievements of the project, some technical achievements related to the scope of today's workshop, the ISA contributions, and let's say a summary of the standardization of the exploitation of the outputs of the project. So TerraMeta, in a nutshell, actually focuses on the investigation of groundbreaking technologies for 6G, demonstrating the feasibility of ultra-high data rate wireless communications, leveraging terahertz metasurfaces. Actually, you see on the bottom of these slides, the way we define the frequencies, which is very much aligned with the literature, what is millimeter wave and what is terahertz, and explicitly in the project, we're working especially as far as the hardware design is concerned. I will elaborate more in the secure, sorry for this, in the sub-terahertz frequencies of 140 and 300 gigahertz. So in terms of the groundbreaking technologies and the metasurfaces, our focus on novel high-performance terahertz hardware to develop, including low-power consumption wideband switches, reconfigurable intelligent surfaces, as well as transmitters and receivers. And actually, we're working on using these design terahertz components to provide advanced network analysis and optimization techniques. Our use cases, actually, we hope to, let's say, impact 6G and especially those specific ones that you will see in more detail. And we're focusing on indoor, outdoor, and indoor to outdoor scenarios to demonstrate at the end of the project, focusing on a real factory setting as well as a telecom testing field. In terms of vision and technological advances, first the vision, the smart wireless environments and enabled by the technology of metasurfaces, or reconfigurable metasurfaces, which give us the capability to program over the air the way that the signal propagates. The massive scale communication with all these devices, which are expected to be rather easy to deploy in certain applications and in other certain use cases. Actually terahertz data throughput, holographic beamforming, enabling unprecedented energy focus in 3 dimensions, and joint communication and sensing, which is one of the aspects of this project. In terms of technological advances, the novel architectures for different forms of RISs, transmissive and reflective RISs, including those RISs that are capable to sense the signal that impinges on them, the design of materials and electronical components that support terahertz operation while focusing on the low fabrication cost and the lower power consumption, and of course, the design of signal processing techniques for those metasurfaces designed within the project, focusing on applications related to communication, localization, and sensing, as well as we have components related to the design of terahertz ultra-massive MIMO techniques and terahertz Taylor network architectures. The project is actually shaped around four main pillars, which you see in this slide, which is one, the terahertz components. Number two is the terahertz metasurfaces. And number three, the signal processing and the network design. And number four, the characterization on modeling, both of the fabricated RISs, but also the environments that include them. So the pillar one will contribute to the development of RIS, as I said before, using the outputs of pillar two, and the characterization and modeling will be performed in pillar four. The requirements for pillar three will set the design specifications for a terahertz components of the RIS developed in pillars 2 and 3. The outputs of pillar 2 and 4, which are the metasurface and characterization and modeling, will fed and are actually feeding pillar 3 for finalizing the parameters used in the signal processing and network design and optimization. And of course, we have already done quite successfully, we believe, and we will continue doing that in the remaining of the project, the outputs of all pillars to be exploited, disseminated, and used for standardization activities. I will give some numbers in the rest of the presentation. But let me spend some time a little bit to elaborate on this, let's say, family of technologies of multifunctional RISs, just to emphasize that we can use metamaterial and metasurfaces to actually design various forms of metasurfaces, which actually imply certain things about the hardware architecture and actually provide us different functionalities, different capabilities. Right, so it's a matter of decision that we take at the end of the day. Strictly speaking, nothing is passive, nothing is fully passive. Even the so-called passive RIS, to change the state and to maintain the state requires some power, which is quite low, of course. And you will see later on that when we're talking about, let's say, more active kind of designs, things, the metasurfaces require, of course, more hardware, more power consumption. But at the end of the day, this is something to be traded off, right, when we incorporate them within the system. So by going through this slide, you will see on the left, let's say, let's try to scan it over columns. You will see the sensor embedded passive RIS. So this is the notion of using a typical, let's say, let me call them almost passive RIS, where we embed it in with sensors. And the reason of doing that, right, is in order to enable the whole metasurface to send something about the picket signal, probably because we need it in a dedicated application, number one, or because we want this sensing information to be used from the metasurface to enable, hopefully, its self-configurability. So knowing something about what impinges on me as a metasurface can be used for optimizing the RIS and minimizing, actually, the control overhead between among the end nodes. On the left column, if we go down, this T-RIS stands for the transmissive RIS, where we can see a RIS which is being actually illuminated from the one side and actually redirects the signal, re-radiates it on the other side. This is the transmissive RIS and has been successfully used by various people around the world in actually obtaining very nice beam properties. In the middle, you see RISs which have actually receiving capabilities and sensing capabilities. On top, you see this hybrid RIS where Terametra has contributed quite a lot. By the way, transmissive RIS is one of the things that we have derived within the project in the frequencies 140, and we're targeting also for 300 gigahertz. On the hybrid RIS, the technology that has been actually, it's a joint effort of a previous project that has just ended, the ISAC-II and Terameta, on devising actually hybrid meta elements. These are metamaterials that are capable to both absorb simultaneously a portion of the impinging signal while reflecting in a tunable way another portion of it. And actually the idea is very, very similar to the sensor embedded RIS, though you don't need sensors. We're talking about the same, the hybrid meta elements and not, let's say, different protocols within the metasurface to incorporate the sensors with the rest of the metasurface. More details, of course, you can see in relevant papers. I'm not going to dig into it in this presentation. On the bottom, you see a star RIS, which is a RIS that if you actually compare it with the T-RIS on the bottom left, you will see that apart from having this capability of, let's say, providing this over its structure redirection, re-radiation of the signal, it provides this capability of both simultaneously reflecting and refracting the signal. If now we go on the right, let's say column, you see metasurfaces being used to actually replace the RF front ends, the antenna panels of typical antenna array systems, right? So in this way, you could use a metasurface. Actually, this is called the dynamic metasurface antennas or metasurface-based antennas, where actually through dedicated waveguides, you can guide the output, the combined output of certain groups of elements within either receive or transmitter scenes in order to realize transmitters and receivers. So this is what we mean within the project and in the literature, this as multifunctional RISs, where to summarize once more, we imply different hardware architectures, which are accompanied with different capabilities of those metasurfaces with certain actually properties and advantages compared with conventional antenna arrays, for example, with the DMAs. Now, in terms of technical achievements up to now in the project, let me try to summarize them. So we have actually quite actually a large number of outputs in terms of terahertz component design. As far as at the unit cell level, we have actually fabricated an 1-bit transmissive RIS operating at D-band, which is based on CMOS switches. Also, an 1-bit transmissive RIS at D-band uses this technology of phase change material. Another 1-bit RIS at D-band and multifunctional actually RIS at 140 gigahertz and 300 gigahertz, which actually has this dual band and has certain modes of operations. It can operate as an 1-bit transmissive RIS, as a 2-bit this almost passive reflective RIS, and 1-bit simultaneous transmitting and receiving RIS. In the switch design level, we have actually characterized switches based on this technology of gallium nitride on silicon, memory store switch modeling and characterization, as well as providing actually the first available internationally demo of a microfluid switch. In terms of terahertz receivers and transmitters development, we have actually been working on a Schottky diode-based high-speed, high-power amplitude modulator for terahertz transmission, sub-terahertz actually, strictly speaking, at 300 gigahertz. We have actually very promising simulations, and in the actually the remaining part of the project, the goal is to fabricate it. We have been working on design and fabrication as well as characterization of passive RISs with 1, 2, 3-bit resolution. These are the resolution in terms of the states of the electromagnetic responses of the unit cells comprising those metasurfaces, as well as a transmissive RIS, a 3-bit one at 300 gigahertz. And both of these guys have been used on the first channel measurement campaign. You will see some results later on. And we have worked also on the design and fabrication of RIS's active T-RIS-based module at D-band, the first microfluid-based RIS demonstration at D-band that I mentioned before. Also, system and network architecture specification LAN-based simulations have been also performed. We have conducted the first channel measurement campaign at 304 gigahertz with the fabricated passive RISs and the transmissive RIS. And we have actually demonstrated an end-to-end link at D-band with a designed BBU, a baseband unit, from one of the partners together with a transmissive RIS, a receiving RIS, and the respective RF front ends. I have some figures to show you at the end of my presentation. In terms of signal processing for metasurface-aided terahertz communication, localization, and sensing, we have actually worked on channel modeling, provided actually a couple of models, a tripolarized point-to-point communication model with dynamic metasurface antennas, mutual coupling modeling of RISs, and actually the characterization, a generic framework of actually using generic distributions and noise errors and hardware imperfections to see how these imperfections actually impact the performance of a terahertz link. For channel estimation, we have devised a time domain joint beam screen and channel estimation approach at terahertz, a protocol for cascade channel estimation for a MIMO system aided by an almost passive reconfigurable intelligent surfaces. We have actually various algorithms in beam management, hierarchical beam management for both near and far field RISs, beam tracking in near field when we're having dynamic metasurface antennas, as well as machine learning kind of approaches for low complexity beam design. For ultramassive MIMO beamforming, we have already 2 contributions for hybrid beamforming with ultramassive MIMO and low-resolution hardware, an AI-based beamforming algorithm for the transceivers, the multi-antenna transceivers, as well as the risk profiles, a terahertz channel rank enhancement via using RISs, 2 contributions for distributed network architecture with multiple RISs, performance analysis of 1-bit RIS, and actually, let's say, low complexity solutions on real-time optimizing those metasurfaces, as well as optimization and modeling of another technology, which is actually based on leaky waveguide antennas, wideband operation on terahertz, and we actually deployed this technology already to provide multi-user communication, and we're currently working on doing sensing with this technology. For localization and sensing with reconfigurable metasurfaces, we have actually devised an approach for simultaneous localization and mapping with RISs, localization and sensing with a hybrid RIS, the simultaneous reflecting and sensing RISs, 4 contributions for near-field localization and tracking with DMAs, as well as a non-line of sight localization with RIS. And in summary, we have already 74 publications, 10 contributions to HISG's terahertz RIS, and in the IEEE 802.15 Standing Committee on Terahertz. To be a bit more specific in terms of system definition, use cases, and requirements, actually this is our work package 2, which has been finalized. We have the reports ready and they are available online. We have defined actually the different requirements for different use cases that combine terahertz with actually the adoption of RISs. Mainly, we're focusing in this project. These are actually use cases that we're going to demonstrate at the end. I will provide some hints at the end of my presentation. The one is an industrial edge indoor use case, and the other is an outdoor use case, a telecom-based one for a fixed connection at terahertz. We have worked on the way to integrate RISs to O-RAN and 3GPP, as well as to integrate RISs in 802.11 kind of protocols. We have provided actually a link budget analysis using RISs, as well as a lab-based simulator in order to come up with those results to understand how far we could go with the frequencies that we're focusing within the project. The 140 and 300 gigahertz are the frequencies I told you before that we're going to actually shape around our demos at the end of the day, of the project actually. In terms of design, characterization, fabrication of RIS unit cells, we have actually devised a multifunctional CMOS unit cell at W, D, and H bands. You see here, for example, schematically a unit cell incorporating 4 switches and actually supporting 3 different modes, not simultaneously, in a time division manner. Mode 1, where you have a purely reflective RIS, mode 2, where you have a star RIS, and mode 3 when you have a transmissive RIS. We have also designed an RIS Schottky diode unit cell at D band, as well as a modified version for switch integration and 1D bias lines. Other prototypes, we have designed the characterization and 1-bit RIS at D band with planar tightly coupled dipoles. You see on the top right the measured and simulation radiation of the designed wideband RIS when the beam is configured to point in a specific direction. We have fabricated a 31 times 31. This R RIS stands for the reflective RIS, this so-called almost passive RIS with 1-bit unicell, as well as a 3-bit transmissive RIS prototype that was actually used for our first channel sounding campaign. You see here the signal frequency, the beam widths, the aperture efficiency, etc. And on the left, actually, you see the schematic of this structure. We have used, as I said before, our transmissive RIS and the different, in terms of phase resolution, reflective RIS for our first channel sounding campaign at 304 gigahertz in one of the partners' premises. Actually, this has been done together with Time Project presented before. To this end, we have actually characterized the angular distribution of the cascaded transmitter, receiver, and RIS channel. Just to emphasize, you see there that we have used the RIS both as a reflector, but also as realizing the transmitter, right? The beamforming at the transmitter. And we have also performed measurements on the cascaded channel measurement between a T-RIS RIS and DRX. And what we have seen in a nutshell is that indeed, when you're using RISs, you can have enhanced connectivity via the cascaded path that is created by the reflective RIS, which provides the strongest channel component. And we have seen that actually the resolution of the RIS plays, of course, a role in terms of number of stage supporters. And we have actually seen a 5 dB difference in gain between N1 and 3 bit resolution reflective RIS at distances larger than 4.5 meters. In terms of signal processing design, we have actually worked on channel modeling for tripolarized reconfigurable metasurfaces, localization and mapping and sensing with hybrid RISs, hierarchical codebooks for low overhead beam training, as well as distributed optimization of multi-RIS empowered, multi-access wireless and self-free systems, considering or not transmitter and receiver DMAs, as well as beyond Yagolan RISs. To be a bit more specific in the amount of time that I have in terms of ISAC, we have worked on a RIS-enabled SLAM and localization with DMAs. On the left, this is actually a work that was in parallel between ISAC-G and TerraMeta on a SLAM framework, where you see mobile UE transmitted signals that are reflected from the static environment and from the reflective RIS. And the idea is here to be capable, without the intervention of a base station, for the UE to find this position with respect to the reference system of the RIS or itself, and the scatterers, right, objects, passive objects that are within its vicinity. We have used actually a recursive estimation scheme based on an extension of the Poisson multi-Bernoulli stamp filter, and we have actually worked a lot in understanding what are the differences that we can provide. Specifically, this work was frequency agnostic and would be applied actually in the frequencies of interest that we have within the project. On the right, you see a work where we focused on near-field localization at terahertz with a received DMA. And what we wanted to understand here was the performance limits for localization with DMAs. And to this end, we have derived the Cramer bound for the UE spatial parameters, and we have optimized this bound with respect to the hybrid analog and digital combiner. So in a way, we wanted actually to optimize the way that we, let's say, spatially sense the channel, set the receiver beamforming in order to provide lower position error bound within next to the vicinity of an access point that uses the receiver. Going further, very recently, these are ongoing works. On the left, one work that will be submitted in UCAP and another work which is under submission in a journal. On the left, you see simultaneous localization and communication via hybrid RIS. Actually, this is the first work using a hybrid RIS for simultaneous actually communication and localization. The idea here is to focus on a bistatic setup using a base station and a hybrid RIS, where actually the base station wishes to communicate with a UE in the presence of multiple passive radar targets. And actually, what the hybrid RIS is doing is trying to do two things in parallel due to its dual functionality. The one is to assist the communication between the base station and the UE, and the other is through its sensing capability due to its received beamforming in a way to try to illuminate an area in order to be capable to understand in a bistatic mode the presence of targets. The way actually we tackle this problem, we have derived the CRB for the radar target spatial parameters, and we have maximized the downlink rate for the UE while ensuring localization coverage through PEB constraints over a geographical area, not in a specific area, but over a geographical area. And we have seen actually that you can provide actually very good localization properties, we call it coverage, within an area of interest for certain actually parameters that we investigate. I'll leave the details in case when there are any questions. On the right, you see a way that we actually deployed dynamic metasurface antennas to realize in high frequency full duplex nodes. So the idea here is to do simultaneous, again, communication and sensing by using DMAs at the transmit and the receive part. Actually profiting from the fact that in these frequencies, you need to have quite directive beams. You don't need to have any specific self-interference actually system like cancellation to do that. And with the directive transmitting beams, you can actually, and of course the receive informing, you can solve this problem in a very efficient way. So what we're doing here, we do downlink communication with, of course, data signals, and the same data signals that are known to the full duplex node, they are received via reflection of the targets, and we're trying to understand the presence of this target. This is actually a typical monostatic sensing kind of setup with data signals. We have investigated the trade-off between localization and communication, and what's the role of SI cancellation that I mentioned before. And our methodology, we have derived the Kramer-Rao bound for the radar target special parameters, and we have actually focused on an optimization problem, maximizing the downlink rate under a PED constraint for the target position. Before ending my presentation, I would like actually to mention that we have already indoor, in a lab environment, we have actually implemented an end-to-end terahertz link at terahertz band using our transmissive RIS. We have used our BBU, the baseband unit, developed by one of the partners, together with the RF from 10 comprising of a transmissive RIS that has been used both at the transmit part and the receive part. The baseband actually was doing to V-band IQ up conversion and V-band to D-band up conversion, and we have used real-time DSP processing for all the induced impairments. And going further, let's say the fresher generation of this setup was in a couple of weeks ago, 2 weeks ago, in the European Microwave Week in Paris, where we actually provided this demo using a robot. Again, the RF from 10 transmissive RIS used as a transmitter, the receiver, an active RIS using as a repeater now at D-band around 150 gigahertz. You can see on the bottom right of this slide, T-RIS, R-RIS using as this receiver. There have been also the T-RIS being deployed, you see here on the robot. The repeater was on this Eiffel Tower that you see here, and the receiver deployed the T-RIS as a receiver PC on bench. The robot actually incorporated, had 3 depth sensing cameras for 250 times 60 degrees field of view, and the round trip distance from the transmitter to the receiver was around 5 meters, and we have managed by this interconnection of all the elements to have an overall link capacity baseband to baseband at 57 gigabps per second. Before summarizing, I would like actually to mention here that in terms of standardization, TerraMeta has already 3 contributions to this IEEE Standing Committee on Terahertz group, 7 contributions to the ISAC terahertz, which is very relevant to our actually field of work, 2 magazine papers based on ETSI, ISG, terahertz, and RIS. And in terms of exploitation, we have 5 submitted patents. We have incorporated our ISs to one of the partners' system-level simulator. We have used our fabricated T-RIS and R-RIS for the measurement campaign that you saw before that has been conducted together with another project. We have 4 already D-band unit cell designs for multifunctional RISs, 4 switch development for RIS unit cells, and as I mentioned before, the first microfluid-based RIS and D-band, and the first active RIS at D-band. I would like to thank you for your question and hope there is some time for questions. Thank you.
Thank you, George.